Okay, we shall get the talk started. Soon after I arrived at Sonoma State, about 2 years after being here, I was in the position of writing letters of recommendation for some of our students who were graduating and moving on to graduate school. And as time has gone by, I've obviously continued that tradition. But the very first time I wrote some of these letters of recommendation, the students for whom I wrote them sent me a lovely little link to an online cartoon. And this cartoon was highlighting the differences between American and British expectations in terms of referencing. So they gave the example of the American reference, and it said, this student is phenomenal, spectacular, has achieved wonderful things. The only reason they haven't published 7 papers already is that the world is simply not ready for the magnitude of their achievement. And the British reference said, of all the students I've had, this person was one of them. And that was almost one of the highest accolades that could be paid. Our speaker today is a Sonoma State student who is here to tell you about a truly impressive achievement. As part of a program based at CSU Fresno, there are several students each year who take part in this experience at Cern, gaining experience with real research, working with a scientist at the facility themselves. So I think the best way I can introduce our speaker today is, of all the students I've had, Zachary was one of them. Thank you very much. Let's welcome our speaker.
Thank you all for having me. Again, my name is Zach, and I'm a student here at Sonoma State University, and I'm here today to talk to you all about my research experience at Cern working on the ATLAS experiment. So before I get started on what I did there, I want to talk to you a little bit about what Cern is, what the ATLAS experiment is, and how I was selected to go there before I move on to what I did. So, CERN is, in English, the European Organization for Nuclear Research, and it's an institution that was founded in 1954. And they initially set out to do nuclear research, although it doesn't really take place there too often now. It's located right here in Switzerland, right in the northwest suburb of Geneva on the Franco-Swiss border. And in French, I don't know if anybody speaks French here, you can pronounce it. That's where the acronym CERN comes from, is the French version of the name of the institution. Yeah. And CERN's main function now is to provide the infrastructure needed for the high energy physics research, specifically at the Large Hadron Collider. At CERN right now, there are numerous experiments going on, but there are 7 main ones, of which ATLAS is one. There are many small ones that are going on, and there are actually many different smaller colliders at CERN, and people are doing little independent projects there. So, the Large Hadron Collider is massive. It's a 27-kilometer ring that's located 100 meters below the ground, and it extends across the Franco-Swiss border. What it does is it accelerates a proton and an anti-proton beam up near the speed of light. That's actually the number 99 point, all those 9s and then a 1 that it gets it up to. This speed allows the beams to basically move around that 27-kilometer ring at a rate of 11.2 kilohertz, so 11,200 times per second. Due to this extremely high speed of these beams, the particles in there acquire an extremely high amount of kinetic energy. And then when these things finally collide, it produces collisions that happen, or actually it produces about 1 billion collisions per second once it's up to its full speed. So the total energy of these beams in the collider is about 14 TeV, and that's about approximately 7 TeV per beam. So each one of these beams actually consists of about 2,808 bunches of protons. And each one of these 2,808 proton bunches has about 1.15 times 10 to the 11 protons within it. And that sounds like a lot, but if you really think about it, it's very small. It's actually very small size relative to us. Each one of these bunches, each one of these 2,808 bunches, is only a few centimeters long and only about 16 microns in diameter. So very, very, very small. So just how much kinetic energy per beam are we talking here? Okay, so each beam carries a kinetic energy of 362 megajoules of energy. That's the equivalent of 2 10,000-ton cruise ships moving at 30 kilometers per hour and then colliding into each other. Or it's like 2 sets of 450 2-ton automobiles moving at 100 kilometers and then colliding with one another. So that's a ton of energy. Or you can imagine that if you were to detonate 80 kilograms of TNT, that's the kind of energy that would be released in the explosion, or enough thermal energy to melt 500 kilograms of copper. Also, that kind of energy could raise 1 cubic ton, not 1 cubic meter, 1 cubic ton of water, 85 degrees. So how are these particles accelerated at CERN? Well, with a bunch of magnets. But to first start off on what goes into actually getting these particles up to speed, we need to minimize any other collisions that these particles may have with gas within these tubes. So in order to do that, we need to produce a vacuum like that of space, and that's actually about 10 to the negative 13 atmospheres. And in order to get it down to that level, they need to basically pump these tubes for around 2 weeks. So it's a lot that goes into just prepping the tubes. But once they get the vacuum down to that pressure, then they get the ring down to 1.9 Kelvin using liquid helium refrigerators. And the reason they do this is because when at these extremely low temperatures, it will condense the gas and it will cause it to adhere to the walls of the tubes by a process known as adsorption. And this is one of their refrigerator units at CERN, of which there are 8 situated around the 27-kilometer ring. And like I said with the magnets before, there are 50 different types. There are dipoles, there are quadrupoles. And there's just a ton. And those are responsible for accelerating the protons. Okay, so how do we get these particles up to speed? Do we just plop them inside of the accelerator and they just start moving? No. It's more complicated than that. There are actually a few different rings that are responsible for actually getting the particle up to a certain speed and particles up to a certain speed and energy before they can then be injected into the main loop. And so I'll show that here. So this is the first little ring. It's 157 meters in diameter, and this one is 630. And this is the final ring before they get injected into the main loop, where they'll eventually be accelerated up to near the speed of light. So in the tunnels, this is basically what it looks like. It's just basically a tube that's moving around. And on the inside, they're going to show an animation of a proton. This is a single proton. And on the inside, those colored little spheres moving are quarks. So the protons come together at the center of what is known as the Atlas detector. And then when they collide, they release a whole bunch of new particles. So that's what CERN does. We create new particles there. And then the Atlas detector is responsible for helping us see what kind of new particles are created. So if we're dealing with 1 billion collisions per second, this is basically a ton of data, as one can imagine. This is basically equivalent every second to making about 100,000 CDs. And 100,000 CDs, like you can try to imagine it, but just imagine a CD on the floor and then raise it by 150 meters up in the sky. So every second, that's how much we make. In fact, 50 petabytes in raw data are expected to be made in 2018 alone. In the couple years prior to that, it's been around 30 petabytes. So this is going to be the most data taken so far. That amount of information is equivalent to making 50 billion phone calls simultaneously. But so we don't want to cope with that much data being created. So what they did at CERN is they designed a system of triggers. And this trigger system is basically responsible for weeding out the uninteresting events. So at CERN, they want to look at the particles or the collisions that produce particles that are of the highest energy. Because we know about the things that are lower energy. We want to push the bounds and see what could be created there. So that will read out the ones with the lowest transverse momentum inside of the detector. And this whole trigger system will reduce that 1 billion collisions per second down to just 100 interesting events. But that still creates about 200 terabytes of data per year. So where's all this raw data stored, that 50 petabytes of data? Well, there's a 4-tier system that was designed by Cern, known as the Worldwide Lhc Computing Grid. It is basically a network of 170 computing centers. They're situated in 42 different countries around the world. This enables scientists from all around the globe to access the data as it's being created real time. So anywhere in the world, any physicist or scientist can work from their home on their computer and see what's going on at Cern in Switzerland. Now I'd like to talk to you about what kinds of particles are out there that we know about now. So as we currently think now, all the matter that we can see and we know about is made up of things called quarks and leptons. And the lighter a particle is, the more stable it is. And I'll talk about what stability means later. So quarks are the substructure of baryons. And baryons are things like your protons and your neutrons. And those are composed of 3 quarks. And then there are things such as mesons, which are composed of a quark and an antiquark pair. And they don't last very long. They're pretty unstable. And then there's leptons, which have no known substructure at this time, and that would be something such as like an electron, a muon, tau, or like a neutrino. So at CERN, we want to collide baryons. We want to collide the protons, stuff like that, because they have substructure. And when these quarks collide inside the collisions, they produce new particles out of that. So, and then there are things called bosons, which many of you have heard of, the Higgs boson. And they're responsible for mediating the forces in nature. So there's this W and Z bosons, which are heavy particles, and they're responsible for mediating the weak force. And due to their high mass, they're very unstable, and what they do is they decay rapidly. So that means they don't exist very long. They like to break down into new things. So lifetime of a W and Z boson is around 3 times 10 to the negative 25 seconds. So this is this very short lifetime is actually what's responsible for the limited range of the weak force. And this image right here is just the standard model. It lists all the different quarks, the leptons, and then here are your bosons, and the graviton outside the standard model. And then another boson is called the gluon. And a gluon is the particle that actually holds the nucleus of an atom together, holds quarks together. Then there's the photon, which mediates the electromagnetic force. So when EM interaction is happening, these particles are exchanging these photons. So, and then there's the Higgs, which is basically an excitation of something called the Higgs field, which was a humongous scientific discovery. And it is responsible for generating mass through interaction with other particles in the field. And finally, there's the graviton, which is predicted, but it has yet to be found. So, if the lifetime of these heavy particles, such as the WZ, Higgs, are so short, how do we see them? Well, in short, we don't. They cannot be detected directly. The rapid decay means that it makes it almost impossible to detect at this point. But they do undergo a process during their decay called hadronization. And that's when they decay into other particles, which will then decay until they reach a more stable state. So what we have to do at CERN is you have to take this information, what they decay into, and then you have to reconstruct their mass and compare it to standard model predictions and see if they match up. This process is called jet reconstruction. So in this image, you can see this is where the actual collision happens, but then instantaneously, so 5 times 10 to the negative 25 seconds or so, 3, they'll decay. So this is where the theory really goes down, because we don't see this. Then it undergoes the hadronization, which means it's going to decay into particles which we can detect, but they're going to start decaying rapidly too. into new particles until it gets all the way into the detector, which is a series of calorimeters. And then we finally get something called a jet at the top, and that's what we collect and have to reconstruct. So we take this energy deposited in this detector, and we have to reconstruct everything that happened prior. But like I said, that's all you see is the final product. Okay, so what is a jet? A jet is a result of the fragmentation and the hadronization of these particles. So what physicists had to do in order to basically determine what a jet is, they had to design a program called, programs called jet finding algorithms. These will enable them, the physicists and the scientists at Cern, to follow the breadcrumbs back to the original particle that was created in a collision. And it's an extremely complex machine learning algorithm. I had to basically navigate it and try to work with it, but I couldn't even begin to tell you how many lines of code there were. It's amazing. So in the collisions, this is basically what happens. You have a bunch of different particles that are created, but then the jet finding algorithm says, okay, this little region is called a jet, and this little region is called a jet. And then we have to interpret what those jet means, and that's where the theory comes in. So what do those jets actually mean? And so there are some difficulties in reconstructing this, as you can imagine. You're just taking a product, and then you have to work backwards into things that can't even be detected and try to figure out what they were. So in order to do this, you need to be extremely precise with the measurements of the energy in the detector. They must be within about 0.002% of the real value. So it's very precise. So due to the sensitivity of these machines, what you're going to get is unwanted data. Just alone, for the tidal forces of the full moon can distort the ring radius, that 27 kilometer diameter ring, distort the radius of that ring by around 0.15 millimeters. That doesn't sound like a lot. It sounds like nothing. It's so small. We would never measure or notice that. But what that translates to is around a change in beam energy of 10 mega electron volts. And also in Geneva, I don't know if you guys know this, but they're big on public transportation. There's trains running all up along on the surface above the collider. But as the train's running along, it actually induces a current, and this current flows down 100 meters into the ground and goes into the ring, and that current alone can change the beam energy by 10 MeV too. So yeah, it's very, very sensitive. And this graph right here is the mass of a Z boson, and it shows the precision with which we know its energy to be. So yeah, I think we're doing, it matched the standard model prediction very, very well. Now that I've talked to you about CERN, I want to move on to what the ATLAS experiment is. So the ATLAS experiment, as I explained, takes place at the Large Hadron Collider at CERN. And the ATLAS experiment is a collaboration of people from many different parts of the world. So they're from 38 different countries and 174 different institutions. And they're searching for things like dark matter candidates, extra dimensions, new particles, and just generally physics beyond the standard model. So they're continually trying to push the frontier. And the ATLAS collaboration was one of the collaborations along with CMS, which was responsible for the discovery of the Higgs boson. And ATLAS has 3,000 scientific authors publishing their findings. So this is the ATLAS detector. It is huge. It is a 46 meter long, 25 meter high, and 25 meter wide detector. It's amazing. It weighs around 7,000 tons, and it's the largest volume particle detector ever constructed. That's made out of metal and stuff. There's another one called Ice Cube, which is in the South Pole, and that's made with ice. So they put detectors down into ice, and it's a different way to study particles. It's a different type of detector. So that, like I had mentioned earlier, is where the particle beams collide, right at the center of that thing. So the collision, like I had said, creates these new particles at the center of the detector which fly out in all different directions. So in order to make sure that we can get all of the information, they made sure that it covered nearly the entire solid angle of these collisions. So this is a picture I took at Cern in the Atlas building. So this is the main Atlas building, and it is a 5-story tall building, but they would call it 4 because in Geneva they label the floors as the 0th floor up to the 4th. So it's a 4-story building, but if you were to stand at the base right there, that's actually the size of the detector. That's how big it would look if you were standing at the base of it, so you can just get a feel for it. So, did I go underground to see the collider? No. They were running the LHC when I was there. And they don't let anybody go near it while it's running. Cern has set a dose limit of about 15 millisieverts per year with the possession of a radiation badge. I don't have one of those. Or 6 millisieverts per year for other staff members. So while the LHC is taking data, it produces an enormous amount of radiation. If you were to be down there while they were taking data in some parts, you could acquire around 100 millisieverts per hour, when the maximum dose for someone with a radiation badge is 15 millisieverts per year. So it's pretty dangerous. But I did get to go down and see the old collider. There's a system, a network of tunnels that runs through the entire CERN compound. It's amazing. I mean, you can get lost in there for hours. I personally explored, a fraction of it, and we had spent easily 30 hours in it over the course of 8 weeks. It was really cool. But yeah, so I did get to go see that. So how did I get to CERN? By plane? No, I had enrolled in an online particle physics course through Fresno State in the fall of 2017. And this is a thing that has students from 17 different CSU campuses. So these students from 17 CSU campuses will enroll in this course in the hopes of receiving something called the NSF-IRES award. And then there's another 5 that are chosen without the funding. This award allowed me to travel to and live at CERN for 8 weeks in the summer, and then I got to travel Europe for a few weeks afterward, which is a part of the stipend that I got. On the second student from Sonoma to go, we had a student 2 summers ago, Michael Dobbs, go with the NSF award, and then luckily we have another student going next summer with the award as well. So it's very exciting that we're having students from Sonoma, a small program, be able to do this. The program is run by Dr. Yongsheng Yao from Fresno State. He was actually my lecturer in the fall of 2017, and he was responsible for choosing who could receive these awards. He wrote a grant to the NSF, received $250,000 to support 5 students each summer from 2015 to 2018. And he was responsible for choosing a mentor for me at CERN, whose name is Dr. Gabriel Palacino from the University of Indiana. So now that I've given you an introduction to CERN, Atlas, and the different particles that are created there, I would like to introduce my project. And it's quite a mouthful, but bear with me, I'll try to explain it. The actual project title is to study the impact of input granularity for hardware-level triggers using an iterative jet finding algorithm. So this jet finding algorithm I talked about, that's what I'm using.
Hey, can you go back?
Yes. Very fun. Yeah, it's a long title. Take your time. Well, when he said it to me, I'm like, what? That sounds hard. Yeah. Are you good? Okay, before I talk to you about my project, I'm going to give you a little introduction to why this project came up. So, in any collision at the LHC, in the middle of the Atlas detector, there are 2 types of jets that are produced in copious amounts. They're ones produced through QCD effects, which have a low transverse momentum, and there are the boosted jets, which have high transverse momentum. These QCD jets are produced from light quarks and gluons, and when we reconstruct them, they'll give us Gaussian distributions. These are the ones that are uninteresting to us. And then the boosted jets, which are produced from heavy particles such as the top quarks, the WZ Higgs bosons, are the ones we're interested in, and they have the high transverse momentum. And then when we reconstruct these things, they'll give us Gaussian 2 or 3 peak distributions. And what we're really looking for at Cern is the reconstructed data that gives us the multi-peak distributions. And the reason for this is because the multi-peak distributions indicate jet substructure. And jet substructure means that there were a bunch of different particles created once the protons collided, but they decayed afterward. Right now, the problem is, at the trigger level, we cannot distinguish between what these low transverse momentum jets look like, the ones that are uninteresting, from the interesting ones with the high transverse momentum. So the goal of my project is to determine whether or not I can look at, or whether or not we can distinguish between these low energy particles from the high ones at the trigger level. Yeah, so like I said, that's what I tried to do. I need to see whether I can discriminate between the QCD and the highly boosted jets at the trigger level. In order to do this, we would need to drastically reduce the number of inputs to the trigger, which means the amount of information passed to these triggers at any one time. So the way that my mentor had led me down the path to do was to use these two types of topological clustering techniques, the 420 and the 422, which are shown down here. So what a topological cluster is it's basically a cluster of energy in a region of the detector with a magnitude of transverse energy that's greater than or equal to at least 4 times the background noise that's surrounding it. This little region is called a seed. And the outer regions of the topological clusters are from many different sources that include radiation, there's electronic noise, or pilot noise from other collisions that are basically going to skew the results. So the 420 clustering technique is currently used during jet reconstruction. And this one takes the outermost regions of the topological cluster. So like I said earlier, this is just a representation of what it would be like. So let's say this region was 7 times greater than the background, the ones around the edge. It would choose this to be the seed, and then it would basically take the region all the way out to the point at which there's something 7 times less than it. So the 420 takes the background. And then there's the 422, which rejects the background. So I had to set forth to determine basically which is better. Okay, so the jet finding algorithm I had been working with at Cern is an anti-KT clustering algorithm known as FastJet. It's a sequential clustering algorithm, and they told me it's very clean and simple. It's fast. It's very fast, so it's a good candidate to use these sort of algorithms to try to reduce the number of inputs because it needs to happen rapidly. It reduces the amount of smearing of a jet's momenta due to noise. So as you can see here are the old jet finding algorithms that were used, and you can see the distribution of momentum of these particles is pretty wide. But with the anti-KT FastJet, it gives us more certainty as to where the actual momentum of these particles lies. Their terms in here are associated with ideal cones, which really simplifies their determination, meaning that what the jet finding algorithm determines to be jets is circular. These other ones aren't circular. They're just a cluster and a mess. And this jet finding algorithm allows for something called the binning of the two topological clustering techniques, the 420 and the 422. But most importantly, it will reduce the number of inputs to the trigger. So what is the binning of topological clusters? So, first, each topological cluster has a characteristic vector associated with it. So that tells us about the kinematics of that little cluster. And within a given detector cell, there can be many topological clusters. So what binning does is it takes the vector sum of the topological clusters within any cell and replaces it with a single vector instead. And like I said earlier in the previous slide, this helps us to produce circular jets, which will clip lens-like regions out of the soft lens. So that means that the hardest, the most high transverse energy particles are going to be the ones that dominate. So like this green one right here, it clipses this region out of the purple one, meaning that it has a higher energy than it. So they stand out very easily, because that's the ones we want to look at. So the data I used to try to do this was a simulated Z prime particle decaying to a top anti-top pair. A Z prime is a theoretical particle; it does not exist, but there's a theoretical mass, and we know basically the mechanism by which it should decay if it does exist. So that's the Z prime going to a top anti-top channel. With this data, like I said earlier, we only want to look at the jets who have the greatest transverse momentum. So in order to look at them, I had to look at a parameter called rapidity, which is an angular separation parameter. And this allows the measurement of separation between particles and jet constituents inside of these collisions. So it tells us how far apart the jets are. Eta in the rapidity is known as the pseudo-rapidity. And it is the angle between the particle trajectory and the positive beam axis, and it does not depend on the energy of the particle. And then the delta phi from the rapidity is an angular separation parameter which is orthogonal to the beamline. So my goal now is to say, okay, I need to compare the effects of binning those two types of topological clustering techniques with the jets whose transverse momentum is the greatest, and also compare their masses. So that's step one of the project. Is the 420 or the 422 clustering technique the better representation of transverse momentum in mass? And does the binning of these two clustering techniques change the values of transverse momentum and mass? And if it did, this would be bad. That means that we can't reduce the number of inputs, because the binning is, like I said earlier, what was responsible for reducing the number of inputs to the trigger, that explicitly. So after a whole bunch of work, this is the result that I got. So this is a comparison of the transverse momentum of the leading jets, or those with the greatest transverse momentum, to their respective backgrounds using the unbinned 420 and 422 clustering techniques. As you can see, there is a difference between the 420 and the 422 clustering techniques right off the bat, even with unbinned data. You can see that with their means. It's 922.8 GeV mean of the jets whose transverse momentum is greatest, and then you have a background, which is all the other stuff around the interesting stuff, which has 92, and this one is about, 981? Yeah, that angle, about 981, so there is quite a difference here. Now this is comparing the transverse momentum of the leading jets to their respective backgrounds using the binned 420 and 422 clustering techniques, which is the one that reduces the input to the trigger. And as you can see, still there is a difference in the binning between the 420 and the 422. So my mentor, after looking at these things, at the different clustering techniques, had decided that the 422, which is the one that rejects background, is the more accurate representation in this jet finding algorithm. So from this point forward, I'm only going to be talking about the 4-2-2 clustering technique, which, like I said, will reject the background. He didn't explain why. He just said this is the direction you need to follow now. I'm guessing because it matches up better with what he was expecting. Okay, so these two graphs are the comparison of the transverse momentum of the leading jets to their respective backgrounds. And this one compares the unbinned version of the 4-2-2 to the binned version. And like I said, if the two means of the transverse momentum of the regions of interest are too different, that means we cannot reduce the number of inputs to the trigger. So as you can see, they're very close to one another. He said close enough. So the difference here is this one's 922 for the unbinned, and then bending them changes it by about 3 GeV. And I guess there's other stuff they can do to help correct it, but we just wanted to get it pretty close. And so that's good. And then with the mass as well, it barely changed the mass calculation between the unbinned version of the 422 and the binned. And like I said before, these two graphs are comparing the jets of interest to the background that they're surrounded in. So that's good. We should be able to reduce the number of inputs to the trigger because it does not seem to affect the transverse momentum of the jets or the mass too profoundly. That leads me to the second step of the project. I needed to determine whether or not it's possible to distinguish between the QCD and boosted jets at the trigger level. So we got the confirmation we needed, and it's time to move on to the question at hand that we set out to determine. So in order to try to do this, this is a lot of writing because it's pretty heavy, but we needed to utilize something called the energy correlation double ratios. And these double ratios can measure high order radiation from the leading order substructures, so the ones with the highest transverse momentum. They detail the relationship between the angular separation and energy constants of the jet constituents, so the subjets that are created in the collision. They enable one to measure only the highest transverse momentum constituents, and they tell us how they relate to the ones with low transverse momentum. So they help us to see which are the higher, which are the lower. And then they also reveal how well any given jet can be described to have n subjets and not n-1 subjets, which is very important. But most explicitly, these energy correlation double ratios do not require the explicit identification of subjet regions in a detector. So it's a way to identify a jet as having substructure or highly boosted without having to directly see it. And here they are. These are the two energy correlation double ratios, which are composed of these things. Yeah. So step 3, I needed to find out which energy correlation double ratio provides the greatest resolution. Which one is going to help us to see, or which type, the C or the D type, is going to help us to see these substructures. And that's called probing jet substructure. So after a bunch of more work and coding and sitting in a chair for many hours a day, we found that for the C2 and the D2 type of the bin data, right, that the C2 could actually provide us with a way to determine what the high transverse momentum jets are with substructure from their, maybe it's vice versa. This is the high transverse momentum jets with substructure from their backgrounds. And the D2, on the other hand, is pretty close. So that separation right here, the background from the ones in question, is a way that the jet finding algorithm could identify that there is substructure present. So yeah, the C2 wins. So here is my conclusion. I was only able to test the energy correlation double ratios for n equals 1, which means that there's just one distribution, which is uninteresting because it matched exactly what you'd expect. And then I was able to do the n equals 2, which correspond to the C2 and D2 energy correlation double ratios I found. I ran out of time to do the n equals 3, so it is available at Cern on the Indico side for people to pick it up where I left off and continue further. And he told me that he thinks that the energy correlation double ratio, due to the ability to provide some resolution, could be a good candidate to input into, because I had to write the code for it, to input into the, on top of the other stuff, input into FastJet, and maybe we can start using it. But unfortunately, my research isn't even relevant until around 2030 because of the time frame that these experiments take place. The upgrades that they do take long periods of time, so there's different phases that they do. And so the technology would kind of have to catch up to us to be able to do this sort of stuff at the trigger level. But it is, he says, probably possible. And thank you.
I think hadronization would make a great band name if we ever get to start with physics. You have questions for our speaker? Yes.
Could you go back one slide, please?
Sure.
First of all I can say is, wow, you know, I'm an amateur, so this is way beyond my pay grade. But congratulations.
Oh, thank you. Thank
on
you.
your success. It looks like you satisfied your mentor in terms of providing
Yeah.
good effort. So
I hope so. Thanks.
so what's that?
I said I hope so. I hope I satisfied him
Well, it sounds
well
like
enough.
you did. But I am, I think, smart enough to ask an important question. You're trying to determine substructure, right? That's the key, right?
Or how to identify substructure.
Okay. But this whole thing with the word that I'm stuck on is expectation. You see, that brings me great concern about confirmation bias. Uninteresting match, a single jet expectation.
Right. So, like I said earlier, when you have to reconstruct jets, you expect particles, right? So these theoretical particles in the standard model, like the WZ Higgs, they're expected by scientific data to be a certain mass.
Yeah, well, that's my whole point.
Yeah.
If you're trying to be objective,
Uh-huh.
but then you bring in this notion of what it should be,
Right.
then it seems to me that just intellectually that gives me pause.
It is concerning, but I think
Because I just add one more thing. When I saw the movie on the Higgs boson,
yeah.
and they ran the data, and the first time it was off, and then they ran the
Right,
data again.
right.
But at this time it was on.
Yeah.
And you know what? I wasn't convinced. I thought it was bullshit. Okay?
Well, yeah, many
But I
people.
got the Nobel Prize.
I've heard that. I've heard that from people, but I think it's the theorist's way of interpreting the data better or designing systems that can measure it more accurately. Because remember, I talked about how precise these tools are. So there's a lot of different variables that go into making sure it's all on par, and they do a ton of different test runs to determine whether it's okay. I don't like that's my contribution
That's
to
an
it.
excellent answer, but you know, the whole thing is you're filtering, and you're trying to find the right parameters to give you the best information.
But there has to be, I think, a good number of scientific data, like strong stuff to back it up. I don't think they're just saying, "Oh, this is a region that matches Higgs." That's it.
Yeah, I think it's a question of how we're using the word expectation.
Oh, right. Yeah, I think that's
so
what it might be.
Like, you know, the model's prediction about what property the particle will have is so reasonably well constrained with an uncertainty. Any deviation from that will not be brushed over, as in, you know, we think, oh, we're going to make it think we want it to be. So they don't mean expectation like, let's make it match what we want. They mean, here's the things I'm expecting, but they would love to have answers outside of the expectation. Scott, do you have a follow-up on that as well?
I'm following up, Tom, on your talk. Number one, this is interesting, and to reference my talk from a year ago on science and society, is that our language that we use as scientists is often using words that have subtly different meanings. In here, I think of the term expectation value. It's a very specific quantum mechanical term. It doesn't. It's the idea of what probabilities there will be of certain outcomes. And so I would say, Zachary, you know, the studies are trying to find out what outcomes you actually get. But expectation values in physics are meant to be, let's think of this as a collider and think of a pool table, right? And your cue ball and how you're going to hit it. And there's an expectation of how often a ball will fall into a pocket or where things will fall. And it doesn't mean that we're assuming that that's the only thing that will happen. It is just knowing the underlying laws of nature. You make a model for how often you hit the 8 ball and it goes over here. And so I want to make it very clear that when you're using language here about expectation, it's not, there is, your point is well taken, which is, this goes back to the petabytes of data. What do you end up parsing to find out for the discovery space, right? And so I'm going with my model, which may not be good at all, but your idea is you're looking at ways of finding events that are events that have interesting physics happening in them.
Right.
And so I've got this. I don't have to look at. Still staying with it. You know how many times I break the ball in billiards, right? To see. I'm interested in the ones where all the balls go into the pockets because something interesting happened there. There's interesting physics there. And so I think we just want to make it very clear that you were not saying, hey, we're going to expect this, we're only going to do this. There is this idea of, well, if we're studying this parameter space that we are deciding is the most interesting, are there other phenomenon that we are not seeing yet? And I think your work is specifically to address this, is to make the most efficient use of the time and which events are we going to pull out and something fascinating happen, including things that we would have never expected in the first place.
Well, that's the point I wanted. It does include the possibility of seeing things that you didn't expect.
Well, also, I didn't mention this in the talk, but the probability of a Higgs being created at any given time during the collision is about 1 in 300 trillion. Yeah, so that's another.
You know, or if I can add, it's a prediction, and the thing matches your prediction. Well, that is interesting.
It's because I'm prejudiced.
Well, yeah, naturally, of course. Okay, well, we see it's not a bias. It's a match.
Right.
What usually happens is that it didn't happen again.
Is that?
Interesting.
Yeah. Or you can choose.
I have 2 questions.
Yeah.
My first question is, what was your primary programming language when you were doing
C++.
C++?
Yeah.
Okay. And then my second question is, where did you gather the data to create your bin values? Did you take that from previous CERN data, or were you taking?
This is previous CERN data, so it was downloaded.
So
There are people who, basically the theorists, who make these simulations, and I took from their simulations.
Okay. So
Yeah, to work with it. It's more of an experimental approach, right?
Okay. So
They do the theory, yeah.
You're doing simulated data versus actual.
Right, because the Z prime particle is a theoretical particle. It doesn't exist as we know it, but we think by standard model predictions that it does.
Okay.
And so they simulated how,
How it would work.
how it would be during this top anti-top channel, because the same particle can decay into many different things. There's different ways it can decay, and that depends on the energy that it sits at.
Yeah.
Right? Okay, so that means that they chose this one in particular, and that's the one I went with. I don't know if it's because it's the most probable one or it's the most highly energetic one. I'm going with, I think it's the most highly energetic because top quarks are the heaviest of the quarks, which means they have the highest energy. So.
I just had a question as a comparison between 420 and 422, and not to go back to the word expectation, but I was about to ask kind of what did you expect to be the winning model when you were taking a look at them originally? Because when you showed me 420 versus 422, I expected 422 would probably be a better candidate for reducing the background noise. And then later on, it got shown with the peaks, and it got shown for the
Right.
Did you guys have like kind of a favorite out?
Yeah. So expectation would be that the 422, it might be advantageous to take that one because it reduces a lot of the background. Right, so you don't take some of that. So it ended up working, right?
Strikes me as the right tool for the right job.
Yeah,
rather
It
than-
does,
Yeah,
but you need to confirm it because, like I said earlier, the 420 is what's currently used at the trigger. I mean, at the analysis level, so at the jet reconstruction level. So can we use the technology that we currently have to do this new job, or the program? No. and that says no, you can't. He thinks the 422 is the one that's better.
And my other question on that was, I took a look at the error bars between 420 and 422, and it seemed like the error bars were larger on...
No, we didn't, well, on the what, sorry, continue?
Just one of the slides were popping up, I just saw what appeared to be error bars showing up,
Right.
and it may have just been an optical illusion, but it looked like...
No, they were.
Okay.
Yeah, what were you saying, they were more profound on which one?
Yeah, it looked like it was more profound on 422, but then I saw the mean data and I saw the values, and I was like, it looks like they got the right values, but it looks like the error is larger.
Well, as you move away from the mean, are you talking about explicitly at the peak of the mean it was larger?
I was looking more towards the extreme edges.
Oh, so that yeah. So
That would
you
make
want to
sense if
take
you cut
you want
down
to take the
sample
ones
size.
that have
Very well.
the more
I just want to make sure I was graphically getting it right. Thank you.
ones that are more dominant. Yeah.
Yes.
Okay, so this might be a question you've already answered in the presentation, but it was just a lot of information, so I wasn't able to grasp everything. So Atlas is the experiment of like colliding particles, and then it collects the data of what the particles are doing, where they're going, and you're looking at that data, and then you're
Oh no, it's okay. No, trying to interpret that data more easily.
Okay. And
Basically, like how can we do it more efficiently? How can we do it rapidly as the data is being received, right? As the data is coming in, can I determine what is a highly boosted jet and a non-boosted jet right away? Because right now you can't do that. We can't determine instantaneously whether or not these two things are different. So that's what I was trying to do.
And
It would save a lot of time and energy. Yeah.
And so, I'm sorry, what exactly is the background that like you are looking at? Is it
Right. So in a jet, there's a range of in a collision, right? There's a range of different energies of particles that are created, and they fly out in these different directions. So in any one collision, you're going to have a whole bunch of different data that's going to be surrounding the one that you want to look at. And so we're looking at the accumulation of these jets and all this data that have the greatest transverse momentum, so the most highly energetic ones, which will correspond to the ones with the highest mass. Okay, does that help?
So it's a terrible analogy, but a lot of people describe particle accelerators simplistically as imagine you want to understand how a cell phone works. Well, one of the ways you can try and investigate how it works is they throw it at the wall and look at all the bits that come out. And think, well, if I throw it even harder at the wall, different things will come out. But the problem is it's not just one brand of cell phone. It's like a Walkman, a CD player, a cell phone. So you can have it all thrown at the wall at the same time, and you've got to try and recreate how it works from that. So you're trying to recreate what you hope is the original event from the sort of detritus, which you can actually measure after the event. So that's why
I should have used that analogy.
it has its flaws. It's just,
it's fun though. Okay.
So is there any sort of potential to create a larger or a more energetic collision? Because you said it was like 0.99999 C, right? Is there like a limit at that point where?
Right. So you know from
really help?
you know from the gamma factor that the larger we get the gamma factor, right, that the more energy we get. And so just increasing the speed, increasing the velocity of these particles even further near the speed of light, so adding the extra 9 at the end, is going to make the 1- difference extremely small, which causes the explosion in energy because the denominator is close to 0, right? So it is very important that even though we're nearing the speed of light, it's like how close can we get? Let's get as close as we can forever, because you make the smallest difference.
Do you know if there's any like Cern 2.0 or anything?
Oh, well, it's just to put it in perspective, just the detector alone is over $1 billion. Okay, that's just the detector, just that one chunk out of that 27-kilometer ring. So these projects aren't taken very lightly. So what they're going to do is they're going to upgrade it. Not necessarily 2.0, but let's improve upon CERN 1.0.
Can you describe the upgrade, like what the difference before and after?
So what they want to do is they want to basically get better magnets in there. And so these magnets, like I said, were responsible for the acceleration of particles. So better magnets means higher speeds, more energy. Yeah, so that's one of them. I mean, there's many different upgrades, hardware upgrades, software upgrades. Like they take place over such a long period of time. It's kind of scary to think about, because it's like I could be working on this thing and then I find out 10 years later it's not going to work because we can't do this, or we find a better way to do that. So with all these people, all these different people working, it's there's so many different ideas being thrown around.
Are these updates happening all at once,
Different phases.
different phases?
So phase 1, 2, 3 over the next like 20 something years. Yeah.
So how long do each one of these things, in other words, how long is it down for these upgrades?
Years.
So if it's down, it's down for 3 or 4 or 5 years?
I don't know how. I think it's a couple years. It could be down.
Oh, okay.
Yeah, I think it could be a couple of years.
What's up?
I have a question kind of related to, you said in 10 years it could be obsolete, somebody could find a new way, et cetera, et cetera. Do you see, especially since you put up there that your research is available on the website, and that a lot of people are coming in, logging into the network and being able to work from home and a bunch of other fun stuff like this, successful across a bunch of countries, do you see a lot of the research that's being done as kind of additive in nature, whereas, say, you discovered that 422 was the way to go, but you don't have the hardware to do it, somebody else has the hardware and the ability to program it to do it, and then somebody else is able to go on and make something more elegant than that?
But that's science, though. That's how
Well,
we
what I'm
progress.
saying. Do you see it largely as an additive, or do you see it kind of as an exclusionary? Like, oh no, this was a terrible idea. We just found a way better way to do it this way. So this
It could be
is
both. Why
different.
not? Yeah. Why couldn't it be? I found a way not to do something with the current methods that we have. That's good.
Fair enough.
PhDs.
Yeah, out of the how many you have, that's good though, because you're narrowing into the one that's going to work, it'd be the most efficient or accurate or what have you.
Okay, well, let's thank our speaker again. If you have more questions,